Hi everyone, Tina here, and today I'd like to talk about forces in motion. We'll be using F equals ma, and I'll include examples that involve pulleys. You'll usually learn about this topic during year 1 of your A-level course. I'll go through some key ideas first, and then we'll look at some examples. So here are some key ideas when you're thinking about forces in motion. First of all, Newton's first law of motion says that an object will remain in the same state of motion, so at rest or moving with constant velocity, unless an unbalanced force acts upon it. When the forces acting upon an object are balanced, the object is in equilibrium. A resultant force, which is the force you get after combining forces in a certain direction, acting on an object will cause the object to accelerate in the same direction as the resultant force. Then we've got Newton's second law of motion, F equals ma. F stands for the net force, or resultant force. M is for mass, and A is for acceleration. We'll use this formula all the time in A-level mechanics. From this formula, you can derive the formula for weight, which is W equals mg. Again, you'll use this formula all the time. W is for weight, M for mass, and g for acceleration due to gravity. You'll use g equals 9.8 meters per second squared, unless stated otherwise. Then Newton's third law of motion. For every action, there is an equal and opposite reaction. So when two bodies interact, they apply forces to each other that are equal in magnitude and opposite in direction. Now that we're aware of those ideas, let's take a look at some examples. Example 1. The following force diagram depicts a particle in equilibrium. So remember, equilibrium means the forces are balanced in each direction. It then shows us the particle and various forces acting on it, and it says, by setting up and solving a pair of simultaneous equations, find the values of P and Q. Now, because we know the forces are balanced in each direction, we can say that the left forces are equal to the right forces. So in this case, Q plus 7 is going to be equal to 3Q minus 5P. We can also say that up equals down, so P plus Q is equal to 7. Now, if we tidy up this first equation, move the Q's and P's over to the left-hand side, it's going to be minus 2Q plus 5P equals minus 7. These are our two simultaneous equations, and you can solve them however you like, but I'm going to rearrange one for P, so make it P equals 7 minus Q, and then I'm going to sub in to that first equation. So that will give me minus 2Q plus 5 brackets 7 minus Q equals minus 7. I can then expand and simplify and solve for Q to get Q is equal to 6. Then I'll sub into my P equation, and that will be P equals 7 minus 6 for Q, so 1. And that's it. Example 2. A particle is acted upon by three forces F1, F2, and F3, given in vector form as these, where A and B are constants. Given that the particle is in equilibrium, find the values of the constants A and B. So again, that word equilibrium, meaning the forces are balanced. In this question, it's probably good to think about it as the resultant force being 0. That's because the resultant force is going to be all three forces added together. And where they're in vector form, we can just add them all together, make them equal to 0, and solve. So that will be A minus 3 plus minus 9B plus 2A 8 equals 0. Solving the top line would be A minus 9 plus 2A equals 0. Gives 3A minus 9 equals 0, therefore A equal to 3. Bottom line, minus 3 plus B plus 8 equals 0, B plus 5 equals 0, meaning B is negative 5. Example 3. A car is towing a trailer along a straight horizontal road by means of a horizontal tow rope. The mass of the car is 1,400 kilograms and the mass of the trailer is 700 kilograms. The car and the trailer are modelled as particles and the tow rope as a light, inextensible string. The resistances to motion of the car and the trailer are assumed to be constant and of magnitude 630 newtons and 280 newtons respectively. The driving force on the car due to its engine is 2,380 newtons. Find, and then first, the acceleration of the car. Now, as you can see, I've drawn a diagram to describe all of the information in this question. And that's always going to be your first step in mechanics when you're dealing with a real-life scenario. Draw yourself a diagram that depicts all the forces. Now for part A, to find the acceleration of the car, in my diagram, the whole system is moving towards the right. So I've used a double arrow for A going towards the right. And I'm going to consider the whole system for part A. So by that, I mean the trailer and the car together. And in my diagram, I'm going to treat going to the right as the positive direction to follow the direction of the acceleration. Now we have all of the forces on the diagram. So let's consider the net force for the whole system, which will be equal to ma due to Newton's second law of motion. I'm going to take any forces that are going to the right as positive. So that's going to be 2,380 plus T. Anything going to the left as negative. So minus 630 minus 280 minus T. All of that is equal to the mass of the whole system, so 2,100 altogether, times by the acceleration of the whole system. Now our T's, or tensions, cancel each other out, which is good, and we can solve what's left to find A. So that's going to give us this. A is 0.7 meters per second squared. Part B, they want the tension in the tow rope. Now for this, we need to consider either the car only or the trailer only. We can't consider the whole system again because we don't want the T's to cancel out this time. You can choose either, but I'm going to choose the car only. Again, taking the right direction as positive. F net equals MA. Just looking at the car, that's going to be this, 2,380 driving force minus the resistance on the car minus the tension. That's going to be equal to 1,400 for the car only, times the acceleration, which we now know is 0.7. If you solve this for T, you get T to be 770 newtons. Part C, state how you've used the assumption that the car and the trailer are modelled as particles. So for this, we've used them as particles because we've assumed that the masses are concentrated at one point, rather than being spread throughout the whole car and trailer, which might be the case in real life. For the next part of the question, it says that when the car and trailer are moving at 12 meters per second, the tow rope breaks. So that means this is no longer part of our diagram. Assuming that the driving force on the car and resistances to motion are unchanged, find the distance moved by the car in the first 4 seconds after the tow rope breaks. So for part D, it's specifically referencing the car, so we just want to focus on the car again. Going to the right is positive, and let's look at the forces. So F net equals MA. We know our forces and we know our mass, means we can now work out the new acceleration. If you solve this for A, you get A to be 1.25 meters per second squared. Now that we know A and we've got some other information as well, we can actually do a SUVAT calculation where S, displacement or distance, is unknown, and that's what we want. Initial velocity is 12. Final velocity, don't know, don't care. A is now 1.25 and T is 4. We find the SUVAT equation that does not involve V, and that's here, and we sub in our values to find S. When we do that, we get 58 meters. Example 4. Two particles A and B have masses of 5 kilograms and 9 kilograms respectively. Particles are connected by a light, inextensible string that passes over a smooth, light, fixed pulley, as shown in the diagram below. The particles are released from rest with the string taut. Calculate the acceleration of the particles and the tension in the string as B descends. Now in this question, it does specifically say that B is descending, but it won't always tell you. So you've got to use a bit of common sense here. B is the heavier particle. So if you think about two particles on a pulley, the heavier one is going to move down and the lighter one is going to move up. Let's put that on there. So B is accelerating down and A is accelerating up. Same acceleration, but different directions of motion. In terms of forces, we've got 9G for the weight of B and 5G for the weight of A, and then tension going up in the string. Now, for any pulleys question, because the particles are moving in different directions, you need to consider them separately. So let's start with particle A. I'm going to choose up as positive particle A to follow the direction of acceleration. Net forces, F net equals MA, and for A, that's going to be tension minus the weight, 5G, is equal to the mass, so 5 times acceleration. Particle B, I'm going to take down as positive. Again, following the direction of acceleration always. F net equals MA. Net force this time is going to be 9G minus T, and that's equal to 9A. We now have two simultaneous equations to solve. Again, you can do this however you like, but I'm probably going to rearrange one of them and sub into the other. So I'm going to rearrange one to get T equal to 5A plus 5G. I'm then going to sub this into 2. So 9G minus the T equals 9A. Expand and simplify. Rearrange and get A to be 2 over 7G, or 2.8 meters per second squared. I'm then going to sub this into equation 1 to find T equals 5 times 2.8 plus the 5G gives 63 newtons. And that's it. Last example. A scientist has set up a device to measure the frictional resistance force between a block B and a rough horizontal tabletop. Block B has a mass of 4.5 kilograms and it's connected by a light inextensible string to a metal sphere A of mass 3.5 kilograms. The string passes over a smooth, light, fixed pulley at the edge of the table so that A is hanging vertically downwards as shown in the diagram below. The string between B and the table is horizontal and the frictional resistance between B and the table is modelled as a constant force of magnitude FF newtons. The system is released from rest with the string taut and with sphere A exactly 1 metre above the ground. Given that sphere A strikes ground 0.8 seconds after it's released, determine the value of FF. Now again, common with a lot of mechanics questions, that's a lot of text to take in. So you might want to go back through and just highlight the key parts. So the masses are useful, and then the frictional resistance, which is a constant force of magnitude FF, released from rest 1 metre above the ground, 0.8 seconds. Now everything in these last two pieces of the question is leading us towards a suvat again, because we're given pieces of the puzzle and we can work out acceleration from there. So we know the displacement is 1, the initial velocity is 0 because it's released from rest, final velocity don't know, don't care, A we do care about, and T is 0.8. And this is taking down as the positive direction there. We find the suvat equation that does not involve V, which is here, and we sub in. We simplify and we solve for A to get 3.125 meters per second squared. Now I've done all of this before even labeling the forces on the diagram. Suvat stuck out to me in this question. But now I'm going to go back to the diagram and label everything on. Particle A is accelerating downwards. Now we know the acceleration. Particle B is accelerating towards the right. There's the weight forces, there's the normal reaction force, and there's this frictional force that they're referring to as FF. Don't forget there's also tension in the string in a pulley system. Now that we have this, again, it's a pulley system. The particles are moving in totally different directions, so we've got to consider them separately. Let's start with particle A. I'm going to take down as my positive direction when I'm considering the net forces. So F net's going to be 3.5 g minus t, and that's equal to 3.5 times the acceleration that we found. We can solve this for t, and we get 23.3625 newtons. We can then use that information when we resolve forces for particle B. For particle B, I'm taking the right as positive. I'm going to do F net equals ma, and that's going to be t minus the frictional force that we want to find is equal to the mass of block B times the acceleration. I'm going to sub in the t value from particle A, so 23.3625 minus FF equals 14.0625, and then we can solve for FF, 9.3, and we're done. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already, and do share this with anyone else who you think might find it helpful. Thanks, and see you next time.